Module 8, Chapters 5.4, 5.5, and some out of 5.6. Module 8, Chapter 5.4 is Logarithmic Functions. The function f of x equals a to the x, where a is not equal to 1, is 1 to 1, and therefore has an inverse. Remember, this is called an exponential function. Find the inverse of f of x. Well, remember, if we have f of x is equal to a to the x, to find the inverse, you let y be f of x. Then you switch your x and y, so we get x equals a to the y. Now, in terms of logarithms, if we're trying to get y on its side by itself, this is the log base a of x is equal to y. So f inverse is the log of x base a. The logarithmic function with base a and the exponential function with base a are inverse functions. That is, if f of x is equal to a to the x and f inverse of x is equal to the log of x base a, then f of f inverse is equal to x and f inverse of f is equal to x. Therefore, a to the x and log of x base a are inverses of each other. Recall that the graph of the inverse function is reflexive about the line y equals x, meaning if you took the graph and you folded it along this line, then the two sides of the graph would coincide. Now, this figure is the typical shape for graphs where a is greater than 1, including base e and base 10 graphs. So your exponential function, if a is greater than 1, starts low and ends high. Your logarithmic function starts low and ends a little bit high. Now, if a is between 0 and 1, then your typical shapes look like this. If a is a fraction, it starts up here and comes down, and it gets closer and closer and closer to 0. This one gets closer and closer to x equals 0, and then it levels out this way. Just sort of as a review, the logarithmic function for a is greater than 1 looks like this right here. Starts down here at a to the negative 1, or 1 over a negative 1, goes up to 1 over 1, 0, and then a comma 1. The function's graph is increasing and continuous on its entire domain. The y-axis is a vertical asymptote as x approaches 0 from the right, and the graph will always go through the points a to the negative 1, comma negative 1, 1, 0, and a comma 1. The logarithmic function, if a is between 0 and 1, is the opposite. It's going to go through a1, 1, 0, and a to the negative 1, comma negative 1. Now the graph of this function is decreasing and continuous on its entire domain, which is from 0 to infinity. The y-axis is a vertical asymptote as x approaches 0 from the right, and the graph will always go through the ordered pairs a1, 1, 0, and a to the negative 1, comma negative 1. Now the domain of each function, remember for logs, the argument, or what you're taking the log of, cannot be negative, and actually it can't be 0. So what we want is x minus 1 has to be greater than 0. Add 1, so x has to be greater than 1. For the second one, the natural log of x squared minus 4, same thing. We need x squared minus 4 to be greater than 0. Now, if you'll remember from doing quadratic inequalities, what you do is you find out where that function is equal to 0. which in this case is going to be 2 and negative 2. So if we were to graph those points on a number line, there's negative 2 and there's 2, then we're going to pick points in between those intervals. So if we pick 0 in between negative 2 and 2 and plug it in here, we would get 0 squared, which is 0, minus 4, which is negative 4. Is negative 4 greater than 0? No, so 0 is not included. Pick a number 3. 3 squared is 9, minus 4 is 5. Is 5 greater than 0? Yes, so we're going to shade that one. Pick something back here. Pick negative 3. Negative 3 squared minus 4, and that's 9 minus 4, which is 5. That one is also greater than 0, so in that case, we shade that interval. These are always greater than 0, not or equal to, so we do our open circles, which means the interval notation is from negative infinity to negative 2, unioned with 2 to infinity. Okay, if we wanted to look at this on our graph real quick, we could come into y equals the natural log of x squared minus 4 graph, and if you'll notice, the graph goes from negative 2 to infinity, and it also goes from 2 to infinity. Now let's do it again. This time let's give the domain, the range, the asymptote, and the x-intercept. Also tell whether it's increasing or decreasing on its domain. Well, the log base 2 of x minus 1, if we wanted to graph a few points, we know the sort of typical graph shape of this, but let's just plug some points. If x is 0, we get 0 minus 1, which is negative 1. The log of negative 1 we can't do, which goes back to, well, the domain, x minus 1 has to be greater than 0, so x has to be greater than 0, so that one wouldn't even make sense to do. Okay, we can't even pick 1. If we did 2, that would be 2 minus 1 is 1. The log of 1 is 0. Okay, if we could go through and pick out more points, or we could just plug it in our calculator. Remember, this is basically going to be the graph of log of x, log base 2 of x. The x minus 1 means we're going to shift it to the right one place. So if we go through and do the log of, I always do that, the log of x minus 1 divided by the log of 2, and graph that, we get our log function, which is that little starts low and comes up and crosses it. There's our 2, 0 that we did on our points. So our graph is like this right here, which is just like the log of x, but we've shifted it one place to the right. Did we cover everything? Domain would be all numbers greater than 1. Range, because the graph goes very high and very low, range would be all real numbers. The asymptote, now remember earlier it was 0, but because we shifted it to the right, technically that graph will never cross that line. So your vertical asymptote is the line x equals 1. The x-intercept is where y is 0, so the x-intercept is the ordered pair to 0. And the log functions are always increasing. Okay, when we graph this one, give the domain, range, asymptote, and x-intercept. Tell whether the function is increasing or decreasing on the domain. So the domain, we want x to be greater than 0. Now this minus 1 is stuck on the end, so domain is going to be greater than 0. The minus 1 means we're going to shift the whole graph down one place. So where we used to have our x-axis to be on there, now we're going to shift that down one place. We know that 1, 0 is on that graph, so now it's just going to shift down. which is where it's going to cross. So our graph's going to come up through here, it's going to cross, and then continue up there. Notice our x-intercept, we're going to let this thing be equal to 0, so we get 0 equals the log base 3 of x minus 1. Add 1 to both sides, so we get the log of x base 3, which means the log is the power, so that is the base of 3, the power of 1 equals x, so x is equal to 3, so technically it goes through here and through here, so our graph would look something like that. We still have a vertical asymptote of x is equal to 0. Now, let's find the inverse of the function f of x equals negative 2 to the x plus 3. Well, remember you replace f of x with y, so y equals negative 2 to the x plus 3. Now we switch x and y, so x equals negative 2 to the y plus 3. Now, if we're trying to solve for y, we're going to subtract 3, so we get x minus 3 equals negative 2 to the y. Divide both sides by a negative, so that becomes negative of x minus 3 equals 2 to the y, or negative x plus 3 is equal to 2 to the y. Now we're ready to put it in log form because we're trying to find the power. So what this says is the base is 2, so it's the log base 2. The y is the power, so that's the log of base 2 of negative x plus 3. The log is equal to the power, so we get y equals the log base 2 of negative x plus 3. Or therefore, f inverse is equal to the log base 2 of negative x plus 3. Now for an example, the function defined by f of x equals 27 plus 1.105 log of x plus 1 approximates the barometric pressure in inches of mercury at a distance of x miles from the eye of a typical hurricane. They give us a formula that calculates the barometric pressure in inches. Number A says, approximate the pressure 9 miles from the eye of the hurricane. Well, x was the number of miles, so we're just going to plug in and find f of 9, which is 27 plus 1.105 times the log of 9 plus 1, which is 10. All right, we're going to plug in our calculator, 27 plus 1.105 times the log of 10. And when we do that, we get 28.105. Now, B part says, the ordered pair 99, 29.21 belongs to this function. What information does it convey? Well, that says if the x value is 99, that means when you are 99 miles away from the eye of a typical hurricane, then the barometric pressure will be equal to 29.21 inches of mercury. Okay, now Module 8, Chapter 5.5, Exponential and Logarithmic Equations. For b is greater than 0 and b not equal to 1, recall that b to the x is equal to b to the y if and only if x is equal to y. If x is greater than 0 and y is greater than 0, then the log of x base b is equal to the log of y base b if and only if x is equal to y. Now we've got type 1 and type 2 exponential equations. Type 1 equations were solved in section 5.2. They are easily written as powers of the same bases. For example, 125 to the y is equal to 5 to the x. We would write both of these as a power of 5. So 125 is written as 5 to the third. So we'd get 5 to the third to the y is equal to 5 to the x, or 5 to the 3y is equal to 5 to the x. So 3y is equal to x, so y is equal to x over 3. But we were able to get them both in terms of the same base. Type 2 exponential equations cannot be easily written as powers of the same base. For example, 7 to the what power is equal to 12. Well, in terms of exponential equations, we need to think about the inverse function in terms of logarithms. Now, our general strategy is take the log of both sides and apply the power rule to eliminate the variable exponents. Okay, so 7 to the x is equal to 12. Well, if we take the log of both sides, we get the log of 7x is equal to the log of 12. Well, the x comes around out front, so that's the same as x times the log of 7 is equal to the log of 12. Well, to solve for x, we're going to divide both sides by the log of 7. So our answer would be x is equal to the log of 12 divided by the log of 7. Okay, so on our calculator, we're going to say the log of 12 divided by the log of 7, which would give us x is 1.277. If we wanted to check it, plug it back in. 7 to the power of 1.277 should be equal to 1.277. Should be pretty close to 12. Now, because of rounding, we didn't get exactly 12, but we got almost 12. Okay, let's take the log of both sides. So we get the log of 2 to the 3x plus 1 is equal to the log of 3 to the 4 minus x. Now, the power rule says let's bring our 3x plus 1 around, so we get 3x plus 1 times the log of 2 is equal to 4 minus x times the log of 3. We can parentheses. So now we get 3x log of 2 plus 1 log of 2 is equal to 4 log of 3 minus x log of 3. Now, if we group our x terms together, we've got to get x on one side. So we're going to say plus x log of 3 to both sides. So we get 3x log of 2 plus x log of 3. Then we're going to subtract this log of 2 to both sides. So we get 4 times the log of 3 minus the log of 2. Now over here we can't combine these, but we could pull out an x, which would give us 3 log of 2 plus the log of 3. And then over here we've got 4 times the log of 3 minus the log of 2. Now to get x on the side by itself, we're going to divide both sides by 3 log of 2 plus the log of 3. Both sides, 3 log of 2 plus the log of 3. So we end up with x is equal to 4 times the log of 3 minus the log of 2 divided by 3 times the log of 2 plus the log of 3. Now we can just go on our calculator. Now we can just go into our calculator and we get 4 log of 3 minus the log of 2 divided by, down in the bottom, let's put a parenthesis, 3 log of 2 plus the log of 3. Now be careful when you're using your calculator, because every time you hit log, it automatically opens those parentheses. which gives us an x value of 1.1646. I'm just going to call it x equals 1.165. Now, if we wanted to check this on our calculator, we could go back and do y equals 2 to the power of, then in parentheses, 3x plus 1. And then the y2, the other side, we could call that 3 to the power of, in parentheses, 4 minus x. And when we graph those, we know that the intersection is going to be our solution. There's the first curve. There's the second curve. We can't see what's happening up there, but let's try it. Second, calculate number 5. Enter, enter, enter. And we get our intersection as 1.1646, which is exactly what we got when we did a pencil paper method. Now, when solving logarithmic equations, begin by noticing the domain of the variables. In some cases, the solution process leads to extraneous values, that is, values that appear to be solutions but do not actually work in the original equation, maybe because they were not even in the original domain. So let's look at this type. This is the type log of x is equal to the log of y. Now, because these are all log of base 3s, one thing we could do would be to try and write them as single logs. Well, over here, because it's the log of this minus the log of this, remember our quotient rule says we can write that as the log of base 3 of x plus 6 over x plus 2. And that is equal to the log of x base 3. Now remember, on the first one, x plus 6 has to be greater than 0, so x has to be greater than negative 6. The second one, x plus 2, has to be greater than 0, so x has to be greater than negative 2. And then the third one, x has to be greater than 0. Well, we need this one because this one fits all three of them, so when we get a solution, it had better be greater than 0. Now, because we've got the log base 3 here and the log base 3 here, the only way those two could be equal is if their arguments are equal. Well, to solve that rational equation, we're going to multiply both sides by x plus 2. They cancel on the left side, so we get x plus 6. On the other side, we get x squared plus 2x. Now, if we subtract x and subtract 6, we get x squared plus 1x minus 6, or x plus 3, x minus 2 is equal to 0. So we end up with x equals negative 3 or x equals 2. But x equals negative 3 is not included in these domains. Therefore, we throw it out, so our only solution would be x is equal to 2. Now, if we wanted to check this one in our calculator, we're going to go up and we're going to do the log of x plus 6 in parentheses divided by the log of 3 minus the log of x plus 2 divided by the log of 3. That's sort of our change of base formula. On the second side, we would get the log of x divided by the log of 3. And when we graph those, we get a graph that looks like that. To find where they intersect, second, calculate number 5, enter. We don't have to guess, and we get an intersection of x equals 2. Notice these graphs don't even exist back here for x is greater than, for x equals negative 3. What about this one? An equation with exponents and logs. E to the negative 2 natural log of x is equal to 1 over 16. Well, the negative 2 natural log of x means e to the natural log of x to the negative 2, which e to the natural log cancel, so we get x to the negative 2 is equal to 1 over 16, which says 1 over x squared is equal to 1 over 16, which says x squared has to be 16, so x is equal to plus or minus 4. Now, if we wanted to just do this one on our calculator from the start, we go to y equals e to the power of negative 2 natural log of x. Close that. The second part says 1 divided by 16. Graph it. Now, when you look at the graph, you don't see that 1 over 16. I'm going to zoom in just a little bit to show you that 1 over 16 is just a horizontal line very, very, very close to the x-axis of 0. We're going to go to window. Let's change our x values up to 5. I think that's going to include it. The first one coming in. There's our e to the negative 2 natural log of x. There's our 1 over 16. Second, calculate number 5. Now the first curve we're on y1, the second curve we're on y2. We don't have to guess. And we get that the intersection is 4. Okay, which leads us to, we had plus or minus 4, but remember the domain x to the negative 2 has to be greater than 0, which means x has to be greater than 0, so we can throw out the negative 4, which is why I did not show. 5 times 1.2 to the 3x minus 2 plus 1 equals 7. What might be easier is if we solve and get just the exponential part on one side. So if we do minus 1, we get 5 times 1.2 to the 3x minus 2 equals 6. If we go ahead and divide both sides by 5, we get 1.2 to the 3x minus 2 is equal to 6 over 5. Now at this point, we can take the log of both sides. So we would get the log of 1.2 to the 3x minus 2 equals the log of 6/5. So now the 3x minus 2 comes out front, so we get 3x minus 2 times the log of 1.2 is equal to the log of 6 over 5. Now we can go ahead and divide both sides by the log of 1.2. So we get 3x minus 2 equals the log of 6 over 5, which is 1.2, divided by the log of 1.2. So we get 3x minus 2 is equal to 1, plus 2 plus 2, so we get 3x is equal to 3, or x is equal to 1. Now, if we wanted to solve this one on our calculator, then we're going to go to y equals and enter it as shown. 5 times 1.2 to the power of 3x minus 2 plus 1. y2 is equal to 7. Graph it, and we get that. Second trace, number 5, enter, 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 and we get a solution of x is equal to 1. Now, for summary, an exponential or logarithmic equation can be solved by changing the equation into one of the following forms, where a and b are real numbers, a is greater than 0 and a is not 1. If your original equation is a to some function of x equals b, then solve by taking the log of both sides. If your equation is of the form the log of f of x equals the log of g of x, then just set f of x equal to g of x and solve that. Or if you get the log of some function of x equals b, then change that to exponential form and solve the function f of x equals a to the power of b. So for instance, if we had solved the natural log of x plus the natural log of x squared equals 3, That's not any of the forms, but if we could get our logs together, that would be the natural log of x times x squared equals 3, which is the natural log of x to the third equals 3. That was our third summary. Let's put that in exponential form. Base e to the power of 3 is equal to x to the third. Therefore, x is equal to e. We get the natural log of x plus the natural log of x squared is equal to 3. Graph that. Find where they intersect. Second, calculate number 5. Enter. Let's move over just a little bit to make sure we're on first curve. Second curve, guess. We don't have to guess, and we get 2.71828, which in fact is e. Okay? What about this one? Solve the natural log of e to the x minus 2 times the natural log of e equals the natural log of e to the fourth. Now remember, these work the same if they're natural logs or just regular logs. Well, 2 times the natural log of e is the same thing as natural log of e squared. This minus means we're going to divide, so it's the natural log of e to the x over e to the second equals the natural log of e to the fourth. Well, because they're both natural logs, what we've got is e to the x over e to the second is equal to e to the fourth. Now, if you'll remember, these e's are just some constant numbers. So we're going to multiply both sides by e squared. So we get e to the x is equal to e to the sixth. Therefore, x must be equal to 6. Now, another way you could have looked at this is the natural log of e to the x is just x. The natural log of e to the second, remember, natural log means find the power that we raise e to, so that would just be 2. And then the natural log of e to the fourth would just be 4. Then add 2 to both sides, so we get x is equal to 6. Either way you go. Now, Module 8 are just some applications from Chapter 5.6. One physical science application, so anytime they're talking about exponential growth or exponential decay, then we use a formula based on e to some power. Another type of problem says nuclear energy derived from radioactive isotopes can be used to supply power to space vehicles. What is the initial output of the power supply? After how many days will the output be reduced to 35 watts? And after how many days will the output be half of its initial amount? Now, one that may make more sense to you, how long will it take $1,000 invested at 6% compounded quarterly to grow to $2,700? Well, if we wanted to run through this one, A is our final amount, would be 27. P is the initial amount, which is 1,000, times 1 plus R, that is your rate. N is the number of times per year that you compound it, which is quarterly, so it's going to be 4, to the power of 4, which is still N, T. And the question is, how many years will it take? Well, that would be 2,700 equals 1,000 times 1 plus 0.5 to the 14. Now on this one, we're going to divide both sides by 1,000. So we get 2.7 is equal to 1.015 to the 4t. Now, taking the log of both sides gives us the log of 2.7 equals the log of 1.015 to the 4t. Now we bring our 4t out to the front, and we get the log of 2.7 equals 4t times the log of 1.015. Dividing both sides by 4, log of 1.015 gives us t is equal to the log of 2.7 divided by 4 times the log of 1.015. Or maybe to get it in a little bit better for our calculator, the log of 2.7 over the log of 1.015 to the fourth. The log of 2.7 divided by the log of 1.015 to the power of 4, which would give us 16.67, which means about 16.7 years. Finally, you are ready to complete this section of homework on My Math Lab. Then, after you've taken notes on each of these sections and have successfully completed the homework from these sections, you will be ready to take the Module 8 quiz.